And we're live once again. So, how is everybody doing? I hope everybody is doing well and okay and are excited for this lecture. Because I know once again, I'm very excited for this lecture. I will go through the usual again. I'll keep it short because there's some people that I know of that are even more excited than I am. So, thank you to the AnalNet Foundation, the European Commission, the Nix Foundation, and Tweak for making these lecture series happen and making them be the way that they are. One interesting side note that I am excited about as well about the infrastructure is the Oncast instance should be faster today. If not, please let me know. But let's hope everything goes well on that end. So without further ado, I will drag Konrad in here. Hey, Konrad.
Hello, thanks, Brian, for the introduction. Do you hear me?
Yes, I hear you perfectly fine.
Wow. Okay, so I still have to figure out how to share my screen, and then
there's a button at the bottom, share, and then you can choose slides.
In theory, I know it works. I just haven't tried yet. So okay. Share screen is easiest with two monitors. I don't have those, but okay, let's go ahead nevertheless. Share screen, select window. Oh, I can share the entire screen. Okay, I'll do that, and then switch to the right one. Let's see if that works.
Yes.
Oh, that's not
we
the
can
right
see
one.
your screen. Oh.
You can see my screen, but you don't see my presentation, right?
No, I see the screen. I see StreamYard, but not the presentation.
So what happened there? Because I had this thing open. Oh, no, not the log.
We're doing this live, guys.
Yeah, we're doing this live, of course. Otherwise, it's not fun. I mean, this is... So Control M should give me the menu, and then I should be able to...
I see slides.
To go to presentation mode. And now, if I put this one full screen...
I won't share, I'm just doing.
Okay, so this should be... Do you see my slides now in full screen?
We see the slides in full screen, so...
Excellent. So finally, all technical problems are solved, and I'll just start. Okay.
Good luck.
Yeah, it's nice to be here in this lecture series on Nix, and unlike probably most people speaking here, I am not a computer scientist nor a software developer nor any of that. My job description is scientist. I'm a researcher at the French National Research Institution CNRS in biophysics. I'm also an associated researcher at the Synchrotron du Soleil, where I help people with interpretation of experimental data. And what I want to talk about today is the role of Nix and Guix in reproducible science. And if I say Nix next Guix, there's a reason for that. I've used both. I've used Nix in the past when my main platform was macOS. A while ago, I switched to Linux, and now I'm more in the Guix world for the simple reason that I have a scheme history, and that's nicer for me. But I think for me, both of these are very nice systems, and they're pretty much equivalent for the purposes of reproducible science. And actually, as long as both continue and steal good ideas from each other, I think everybody's going to gain. So what I will talk about will apply to both, but my personal experience is more up to date with Guix. Okay, so far. Now back to science. So reproducibility is an old topic in science. It goes back to the good old days. Institutionalized science has started in the 17th century. The first scientific institution in the world was the Royal Society of London for Improving Natural Knowledge, which was founded in the 17th century and 1663 to be precise, and on its logo, on its it has its motto was always nullius in verba, which means don't take anybody's word for it. And the idea there was that if you want to contribute to doing science, you can't just claim something. You have to show evidence, and you have to open it up for inspection. It's not enough to say I am an honest person, trust me. So science must be verifiable, and there's a good reason for that, and the good reason is human nature. We have all heard that to err is human. That was Greek philosophers. There is a more subtle issue with I've tried to formulate it diplomatically, that personal biases are often in conflict with the search for truth. So this is things like falling in love with your own theory, having a personal interest from some theory gaining compared to another, and so on and so on. And the scientific method, I mean, from engineering point of view, could be considered an error correction protocol. So you have all these people doing research, publishing research, and all this may be wrong for various reasons. And then you have something on top of that called the scientific method, which is a social process in which the individual errors and biases are eliminated by continuous peer verification. So everybody's looking over everybody else's shoulder. And the idea is that in this way, we will figure out what's wrong and the right things will survive. So this is not so different from how open source software works as a principle. But there's, of course, a condition for that to work, and that is that published claims must be reproducible by others. So I can't go around and say, I've seen a flying saucer tonight, so therefore flying saucers exist. What I have to say is, well, every Monday morning, if you stand at that place on the Eiffel Tower and look in that direction, you'll see a flying saucer. So then everybody else can join in and then check and have an opinion on that, and we can start a discussion. There are many subtle details which I'll skip over. So, of course, if you're an astronomer and you're watching supernovas, they don't happen twice. So not everything is reproducible, but that's the general guideline, is that as far as possible, you should aim for things to be reproducible. So that was the idea 300 years ago. Now, 3 centuries later, what is going to happen? We are in the reproducibility crisis, or as Wikipedia calls it, the replication crisis. So let's do the same for now. So I'll go to the jargon details later on. So what happened? That's an ongoing methodological crisis. That sounds serious, and it actually is in some way. I'll give you a couple of examples to illustrate what happened. And in some of them, you'll see that computing actually plays a role, and that's why I'm talking here today. I'll start with the most recent case in this crisis that has made a lot of noise last year. That was a big study to check the replicability of cancer biology. So these people got a lot of money, and a lot of people work on this to redo experiments, crucial experiments for understanding how cancer works and how it can be treated. And they found roughly that half of them could not be repeated successfully. So either they could not be repeated because something was missing, or they could be repeated, but the result was not the same. I'll move on to something simpler because cancer is really complicated and the issues are very complicated. And I'll just show this because this is of obvious importance. This one is a much more technical one. It's also closer to my own work. This topic is NMR chemical shifts. NMR is a technique for investigating the structure of molecules using something called chemical shifts, which is a natural phenomenon. And this is a standard technique. Many labs have the equipment and gather data and interpret the data. A couple of years ago, some team published in a journal called Nature Methods a protocol for analyzing data with Python scripts to do the work. And the idea was to make people's life easier so they could just run the scripts and didn't have to worry about the technical details themselves. And many people jumped on that and did it. And then 3 years ago now, some people found a mistake in this. Not a mistake, it's more subtle. Actually, what happened technically is that these scripts work correctly under Windows, but not under Linux. The reason being that the Python function call for listing the files in the directory is guaranteed to produce an ordered result in the Windows, but not under Linux. And since the script relies on the ordering returned by this function call, well, it works fine under Windows where it was developed and not under Linux where it produces random results. And it took quite a while before these people noticed that, well, there's lots of papers published which use these. And they may be wrong because people never say if they use Linux or Windows. So we don't actually know. So that may be completely off or maybe not. We have no idea. So this is a case which is close to the topic of today. There is another topic where computing plays a role in a slightly less obvious way. That's a nice example. You can look it up. It's a free article from Physics Today, a very nice summary over a 7-year dispute, heavy dispute of people shouting at each other about supercooled water. Well, the topic doesn't really matter. Both groups opposing each other here were doing computer simulation studies. Each of them had written their own software, and they were in principle calculating the same thing, or so they thought. But they got contradicting results. The question was, how many phases does supercooled water have? Is it 2 or 3? And one said 2, the other said 3. And they basically shouted at each other, said, you're stupid idiots, and so on and so on. The issue was solved, and one side at some point published their code, the other side never did. And at some point, they made a strategical mistake by promising to send their code on request. And they probably didn't mean to do that, but that was too late. And the other side jumped on this occasion and said, oh yeah, I will request it formally, so now we can look at it. And that was the occasion when somebody could actually compare the two pieces of software, which are quite complex, and figured out that they would actually not do the same. And that one side had made a methodological choice, which was supposed to be a shortcut for optimization and which introduced wrong results. Now, the journalist got it wrong in the title. It says it was a coding error. There was no coding error. It was a methodological choice, which the people considered a technical detail. It existed only in the code and was never mentioned in any publication. So before the code got out, nobody knew what was actually happening. And that is actually a very, very frequent situation, even if it results rarely in a 7-year dispute. This one also is a bit scary. Just the title of the paper should be enough to say where the problem is. So there's this group figured out that the analysis of a certain type of experimental data actually got very different results depending on plenty of software version numbers. And of course, you don't want a scientific result to depend on a software version number. So something is wrong there. And this is a very frequent situation, even though people rarely talk about it and publish it. So let's take a step back. Reproducibility actually is a label that has 3 very different incarnations, and it's important to separate them, distinguish them, which people unfortunately not always do. The first one is experiment reproducibility, that the issue is to do an experiment, redo it independently, and see if you get sufficiently close results. And that's what the Royal Society had in mind in the 7th century. And the second issue is statistical reproducibility. There you redo a study using a different sample, like in medical studies, you don't have the same patients as your colleagues across the Atlantic. So you necessarily change the sample, and the question is, does this still give you similar results, sufficiently close to be credible? And the third type is computation reproducibility. And the other issue is, can you redo a computation and get identical results? So as you will guess, my topic is mainly the last one. And if you look at the ongoing reproducibility crisis and all the examples that are being discussed and studied, then experimental reproducibility just doesn't happen. It's not in the list. It never happens. It doesn't mean that it's no longer an issue, but it's something that people have been aware for 300 years. They know that sometimes reproducibility is not there. It's not easy to achieve for good reasons, and they talk about it and they handle it. The 2 others are actually recent. And that's why they caused the crisis, basically. Statistical reproducibility is recent because actually statistics and science is recent, because it could only be done with computers. Nobody does statistical inference techniques by hand. It's just not doable. And computation reproducibility, it's obvious that it depends on computers. And it's in a sense the most surprising one because, well, computation is supposed to be a deterministic procedure. So if you do it twice, 2 + 2 is 4, and it was 4 100 years ago, and it's very probably going to be 4 in 100 years. So what could possibly go wrong? And the answer is, well, if 2 people get different answers from a computation, they actually did not do the same computation, and they don't agree on what is supposed to be computed. And that's a lack of rigor in documenting what has been done. And this is my topic of today, and you can perhaps already guess where Nix comes in there. Finally, a comment on jargon. So there's reproducibility and replicability. I think the dominant use of the 2 terms is the one I'm going to explain here today. Unfortunately, there's people who use them exactly the other way around. So they exchange the meaning of the 2 terms. So that's unfortunate. That's life. So reproducibility is a technical level. It is verification in engineering as opposed to validation. So the questions posed are, has the procedure been executed correctly as described? It is pretty straightforward, and it gives a simple answer. It is yes or no. Whereas replicability is a scientific question. That is the procedure that has been described the right thing to do to answer the scientific question? It is difficult because it requires scientific judgment, and the answer is typically if, maybe, conditional. So it's not the same thing. And in a specific context of scientific computing, reproducibility tests involve running the same software on the same parameters and the same data and check if you get identical results. You're doing deterministic operations, and we check if we have really, if really everything is the same. Whereas replicability studies change something. They use different software, usually the same parameters and same data, sometimes not, depending on the situation, and check if the result is equivalent. So reproducibility is same software, same data, same parameters, same everything. And why do you do such checks? As I said, if it comes out wrong, if you don't agree, then you have computed something else. So reproducibility checks if people really know for sure what has been computed. And that gives the ability to verify the computation. There's no point in verifying something if you don't even know what was done. And it also means that you can then safely reuse these things for other applications because you're sure that this is what has worked in an earlier case. To be contrasted with something that many people confuse, which is robustness. I showed the slide of a paper about version numbers and how they cause trouble. Now, obviously, scientific methods should not be sensitive to such details. Unfortunately, they are. So what you need to do is to do tests. You do robustness tests, and you vary version numbers. You check different versions, different combinations of versions, and you check if you still get similar results. And that is not reproducibility. This is replicability. This is checking for the scientific appropriateness of the procedure. In particular, its robustness. So same software really means same full software stack. And I think in this audience, people understand this probably better than my usual audience, which is my scientist colleagues, who don't quite see the point. And so I'll go over this a bit more quickly here, but just to illustrate my point. What is a computation? That's the question asked and answered by Alan Turing in his famous paper in 1937. So a computation basically means you have a computer memory with lots of zeros and ones, and you push a button, the computer does something on it and produces a new state of output state of computer memory, which is another series of zeros and ones. So that's a computation. From a computer point of view, there's nothing else to it. It's the Turing machine. Now, the human point of view interprets these bits in a certain way, and this is where the trouble comes in. So we typically distinguish between data, programs, and a computation environment. And for example, if you compile a piece of software, and the data is the source code, the program is the compiler, and the environment is the operating system, and whatever it takes to get the compiler running. And the output is the compiled binary. You're probably all familiar with that. I'm just changing labels, and that you know even better. Package building is computation as well, and this is just a generalization of computation, of compilation, right? You have a package source, a build system, and a build environment, and you produce a package. Now, from most scientists' point of view, these three layers look like this. Data is what I care about. It's my research, my experiment data, my analyzed data, my simulation data. This is what my center of interest. The programs I use for that they've typically been written by maybe myself or by my colleagues, people I know more or less, people I could contact, and so on. So this is kind of in my sphere of interest, but not necessarily my focus of interest. And the environment is, well, yeah, I don't care about it. It's just stuff. I mean, I know it works, and it's just there. It's always been there. It will always be there, and it's going to be fine. Now we can imagine where the trouble comes from, right? Yeah, you're right. It's from the environment. Because unfortunately, if you look at the semantics of computation, the importance in the stack is quite the opposite. So data is just zeros and ones for the computer. There's no meaning attached to it. It is the program that reads the data that actually decides how to interpret the bits. So whether a sequence of bits is a character string or a floating point number is decided by the program that reads it. And the next level is that what the meaning of the program is defined by the environment. So the meaning of a Python script is defined by the Python interpreter, and the meaning of a C program is defined by the C compiler. So the environment is actually what is the last word on what everything means, and that's what scientists consider irrelevant or uninteresting and like to forget about. There's one more complication in this, and that is that computation is, as a dynamical systems point of view, it is chaotic. So here on the left, I've changed a single bit. There's a red 0 somewhere there, but this can change almost everything in the output. So there's no limit to that. You cannot know if you change a single bit that can have no change in the output, that can have a small change in the output, that can have a huge change in the output. There's no way to predict this in general. There's no limit on that. That's what it's called chaotic. Putting this together, let me illustrate it from a common situation in scientific computing, which is floating point arithmetic, very, very, very important numerical methods. So this was a mess for quite a while until it was standardized in 1985 by IEEE norm 754. This is universally accepted today. It is precisely defined. It is deterministic operations. You can redo them any number of times and you get the same result. So there should not be any reproducibility issue. In reality, there's plenty of reproducibility issues. And why does it happen? It happens because you can't write software in terms of the IEEE operations. They define a set of operations like addition and so on with rounding modes and so on. No programming language gives you access to that. So it's actually a compiler writer who decides how a formula in C or Fortran or whatever is translated into IEEE 754 operations. And that actually means that if you take the reproducibility point of view of needing to run the same software, and the compiler is an integral part of your program. You can't factor it out. You can't say, I have a Fortran program, and I don't care which compiler I use. You have to care because the compiler makes a decision for you. So the environment matters, basically. And if you look at all the details and what I've shown, the pictures I've shown before, you actually come to the conclusion that reproducible builds, which are important, the important topic in the Nix universe, are actually the same problem as reproducible science if you look at it from a distance. It's fundamentally the same problem. It's capturing the complete software stack of a computation in order to be able to redo it and get the same output from the same inputs. And Nix and Guix have solved it in principle. There's no question about it. They've also solved it in practice for software builds. And the open issue from my point of view is that they did not yet solve it in practice for scientific computing. So I'll end with a short discussion of that because I'm actually hoping that some people in the audience will contribute to solving these issues. So I'm very selfish interest why I'm talking about this here. One issue is, let's put it this way, why can't you just do a data analysis as a package? In principle, there's nothing opposing a package producing a PDF file, which is a scientific paper with figures in there that were computed from the data. And so there's nothing in Nix or Guix that says that a package has to produce an executable binary. It's just a file that's produced by computation. So you could actually do a simulation or a data analysis in the form of a package. One problem is that this would mean everything has to be stored in the Nix store. And that is designed to be a cache for program binaries and actually certainly not good for, let's say, big data. You don't want 10 gigabyte files in your store for various reasons. There's also no support for incrementally updated data sets. That's a very frequent situation in scientific computation that you have several steps, different scripts, different programs. Reading a data file, a structured composite data file, something like HDF5, if you know about this. And each of them picks data out of it and puts new data into that. So the file changes over time, but in a controlled incremental way. And finally, there's no support for sharing and publishing data. You can share the recipe for redoing the work, but if you do a 3-week simulation, you want to share the result and not just the recipe. There are ways this could be handled, and maybe some of you will do something about this. There's ideas which are circulating already. One is the Git of Git and Next, if you know that. Git has the same issue. You can't put big binary data files in the Git repository. So one of the solutions is Git and Next. You store a hash of the file and in a locator, and that's what you put in your repository, and then you have a procedure outside that lets you look up and download the data from the hash. A related idea would be to use IPFS, meaning content addressable storage system, as a backend, and only store the content identifiers maybe in the Nix store or whatever else. It would be a small piece of data then. But yeah, turning this into a usable tool is a lot of work. Another issue that is what I call, not me, situated software. It's a term that has been invented, I don't know, by who, a while ago. Roughly, situated software is software written for a specific situation or use case, as opposed to generic software, which has a wide range of use cases and can be used by many people in various situations and so on. So situated software has a very limited reuse, and a big part of scientific software is in this category. This software that produces the figure of my latest paper is absolutely not adaptable to anything else. It's a huge script that basically says, load this data set, do the following transformation, and produce a figure where one curve is labeled in blue and the other is written in green. This is really not, you don't want such a program in the Nix package channel. There's no point to that. So you would need tools for handling these reproducibly as a Nix package, but you don't want it to be a Nix package in the standard channels. So you need a different way to publish and retrieve such software, which is more adapted to a reader of a scientific paper than to somebody installing software on a computer. And finally, there is a lack of tools currently for a reproducible research workflow, which takes into account the different phases of a research project, which typically starts from interactive exploration. Let's say run a small simulation, look at the results, run a bigger one, or take a small data set, develop a procedure for analyzing it, and then scale up the data set at some point to switch from a notebook like Jupyter Notebook to a workflow, as in make or snake make, and then freezing this into packages for distribution, for building on it. So there are many steps in this process that you want ideally to be handled by tool support in a way that makes the system at every point reproducible. And at the time, there is limited tool support, and all the tools we have do not ensure reproducibility and do not interact with reproducibility-friendly tools like Nix. So that's my conclusion. So we have, with Nix and Guix, we have excellent infrastructure for scientific computing. In theory, it's actually already useful and used by a small minority of scientists. Most scientists do not appreciate them yet enough to adopt them. One reason is that the tools are a bit too complicated. The learning curve is a bit steep, but also they don't really see the advantage because the last mile is missing, and they basically see what's missing before to see that how much of the foundation is already there. So there's a bit of education to be done, but it's also important to cover the scenarios which are not yet covered and actually dominate the world in this way. And I hope you will all contribute in this exercise. So thanks for your attention and listening to questions, and then see if I can switch back to controlled sharing. No, that doesn't do it. Okay. I should be able to stop sharing. There's no.
We can already remove the slides if that's okay.
Yeah, just do that, because for me it doesn't work. I can only retract permission, which is not what I want to do. Okay.
So I will also pull in a colleague of mine, Julien. Jesus, that came out weird. I'm sorry. So hello, Julien. And yeah, so there is already one question coming in over, or wait, there's multiple questions, but there's one on Matrix by A. Kenji, and they are asking, what is the percentage of publications that in your definition are reproducible at the moment?
depends a lot. It varies a lot from one discipline to the other, and it obviously depends on time. So 15-year-old publications are almost zero reproducibility. In my domain, which is computational biophysics, protein simulations, I would say it's 0.5% at best, which is reproducible today. And the reason is that this is a field dominated by long simulations running on supercomputers, and there's absolutely no tool support for doing parallel computation on weird platforms in a reproducible way for now. There are domains which are more concerned in the sense that there's more public interest in watching these things, and I've been told that some domains are now at something like 10-15% of reproducible papers for the most recent ones, but it's a small minority.
But it's slowly but steadily growing.
It's increasing, yes.
Okay, nice. Then a question by Matthias. Do you think a channel with reproducible Nix scripts should be attached to a journal, such as, example given, Rescience? See?
Yeah, well, Rescience is a journal I've co-founded, which is a bit unusual. It's an online journal for replications in computational science, and we require them to be reproducible. Now we check reproducibility by reviewing. So the reviewers are supposed to check, yes, I can reproduce these results. And we've already figured out that 2 years later, that may no longer be true. So yeah, this would be a nice opportunity. And we have discussed this for introducing tools like Nix or Guix and or Docker containers or whatever else. And for now, our stance is that we kind of encourage people to use such tools if they want to. We don't want to make it a requirement because for many people, the technical overhead is still too much. It's still not user-friendly enough. And if we make this a requirement, we'll simply get fewer submissions. So that's not quite the point. But we do want to move towards such a way, towards such a situation. And as I said, we really need better tool support to get to the point where the average scientist would be willing to do the necessary steps to make it happen.
I'm just quickly rearranging my windows to read the chats a bit better. Julia, do you by any chance have any questions?
Yeah, sure. I mean, follow up on that topic. Nix has kind of a mandate to help software tooling and doing reproducibility on the software side. What can we do to kind of get these tools in scientists' hands in a way that's more usable, more user-friendly? Like, what are the top things you would tackle?
Well, I think there's basically two issues I hear when I try to convince people. A very frequent problem is say, well, I need this exotic software X and it's not packaged, and I can't package this because it's too complicated to package. And in most cases, this is some Python package which uses some exotic build system or its own sub package manager, all these kind of things, or it has 25 dependencies which are hard to package, or it doesn't build even. I mean, there's Python packages nowadays which you can't even build from source easily. So basically, you have Python packages that use Conda, otherwise we can't help you. So I don't really know how to tackle this best. I think maybe the best vector of attack would be to convince the developers of such packages to do the work and to make things more friendly for packaging with Nix. Ideally, do it themselves, but at the very least, not make it more difficult. So I think that it's probably easier to communicate between the Nix community and Python developer community. That should be easier to communicate than with individual scientists. So this would help a lot. Having simply even specialist packages available for ready installation. And then, yeah, I think the next thing would be if you come up with some simple tooling that lets you make a specialist package from something like a script or a Jupyter notebook, and even for straightforward, simple cases, that would cover a lot of ground, because as people discuss a lot the complicated cases, but there's plenty of science done with a single Python and Jupyter notebook. So if you can handle those, you'll get a lot of adoption, and that would help get the other people on the train later on then. So basically, a command line tool or whatever that says, here's my Jupyter notebook, package, wrap this up into a Nix package.
There is an interesting tool that Tweak developed called Jupyter with that kind of does that. You can define like the Jupyter environment that you want, and then you get an environment with all the packages that you need, and Jupyter in there as well, which is pretty nice.
Okay, well, that sounds good. Do some advertising for that, and
just did it.
Yeah, exactly. So that's exactly the kind of thing we need, I would say. Yeah.
Okay, cool. Over on Oncast, Joff R asks, it seems clear that Nix and Guix can help with reproducibility. Can it also help with robustness?
Yes, definitely. Because the nice thing about both of these tools, they both allow, let's say, variations on environments in very, very different ways. So that's really one where the two differ quite radically in their approach to it, but both allow to do it, and this is important. Just the very possibility of having two versions of the same package on the same computer at the same time is so important for this. So, but again, there's no good tool support, as far as I know, for actually doing experiments. To give you an idea of what would be nice, I don't have a pointer right now, but there's a software package called Version Climber. You can look it up by Google under that name, which is specifically for Python environments. It's for virtual Python environments. And it basically takes a list of version numbers for all the dependencies, and it loops over them, and it installs all the environments and runs the program and sees if runs a script and sees if the output is the same. This at the level of Nix and Guix would be a lot more useful, because quite often you have dependencies which are not in Python at some point, and then that's the old problem with Python package managers. As soon as you have a C dependency, they break down, and it's always the case. So they're not really sufficient for real life exploration. But I think there's a space to explore there for automatically testing robustness, much like continuous integration. You would do a scanning for version numbers.
Yes, thank you. On Matrix, Stringfield asks, have you used BioNix before?
Which one?
BioNix.
No, I've heard of it. I think it's a bioinformatics collection of packages. Yeah,
highly reproducible bioinformatics pipeline.
I'm doing biophysics, not bioinformatics. So no, the answer is no.
And we'll go into the next one. Matthias asks, on Matrix, would you think that the dominance of situational software in science is also a consequence of things not being reproducible by default? No, I don't think so. It's really it's the starting point of every new scientific study is situated software. It's what comes with a paper. It's only then when a method that is published in a specialized script becomes more widely interesting, taken up by other people. It's only then that people get together and say, okay, let's factor the common method out into a reusable package. So this will never go away. We'll always have at the leaf of the tree of software dependencies. We'll always have situated software. I think this is not a default. It's the way things work. It's how new methods come into being. So I don't think I've heard people say we should get away with it, and every small script should be reproducible, and all software authors should ensure maintenance of their scripts for their papers. I think this is completely unrealistic, and I don't think we should aim for this now. That makes sense. Matthias asked another question. There's probably also an educational effort necessary to get someone up to speed with tools like Nix. Do you have any idea how scientists and Nixers can connect to help each other out? Are there interesting conferences or online spaces to join as well? Yeah, it's tough. I think the best audience is those scientists who are already interested in doing reproducible research. So they are aware, they're looking for a solution to a problem, because the majority of scientists at this time is basically waiting for the rest of the world to provide them with a solution, and in the meantime go on doing business as usual. So most people don't consider themselves concerned right now, but there's a small set of people who are interested in this, and I think that they are the key audience for any educational measures. Unfortunately, there isn't much in terms of conference. It's a small meetings. I know, for example, there's a field that is very, very well interested in this is neuroscience.
I know that they have at one of their big conferences, they have a special track on reproducibility each year. So that would be a good point to attack, for example. You can look it up, the Rescience journal. We do a special number every year from this reproducibility track. So you see who is running this, who's organizing this, contact these people and offer them a Nix training. I think that's probably would be a good entry point. Other one, yeah, it's difficult. I mean, for most people, the gulf is quite wide from people who they have their tool set on their computers, which is absolutely not reproducible, but that's what they know to use, and they are effective and efficient with that, and they just want to continue using that. And they're basically waiting for someone else to turn their tools into something reproducible, and they don't have to change habits. It's not going to work, but they're dreaming of that. So then they're not going to listen to you. So yeah, you have to capture the most receptive audience, and I think for now it's the reproducibility research community.
Okay. Again, for Matthias on Matrix, do you see awareness on political/funding side growing for Nix type approaches?
I wouldn't say that because that's too technical. There is a quite serious awareness in the what is called the open science movement. So open science goes way beyond computation, of course. Is an ongoing movement that says that science is there for public benefit and should not be hidden behind paywalls and strange conventions and conferences and so on. So whatever especially public science produces should be accessible to the public. And everybody should be able to access the material with just articles, but also code and data. And everybody should be able to look into this, hack on this, and so on and so on and so on. It's a kind of the generalization of the open source and free software idea to science with some adaptations. And science funders have jumped on this and have said, yeah, actually it's true, man. We are paying money and we want this to be effective. To the point that here in France, for example, open science is now a legal obligation. Since December 3, 2021, there was a law passed that says all French public science must be open now. Now, of course, this is typical politician approaches. They have decided to make it open as if the law was sufficient to do it. I mean, nobody knows how to do it, but it's an obligation. So, but again, I mean, that sets the idea, and this has changed a lot. And I've seen that in my mailbox. The number of requests for seminars on reproducible research has multiplied by a factor of 10 since then. So, yeah, politics sets the wider goal, and now that your job, or you're together with people like me who are kind of in the middle way, is to make the link and say, yeah, Nix is good for open science. But I mean, you can't expect politicians to make that link.
No, that makes perfect sense. Before continuing on, Julia, do you have anything else?
I mean, a quick question would be, I'm hearing a little bit of frustration with reproducing Python in general. I say this kind of tongue in cheek, but is it time to retire Python for scientific research, or do you think that one's going to stay?
Oh, you're not the first one to raise that question. My colleague, Rescience colleague Nicolas Rogier, my co-founder Nicolas Rogier, once said, well, actually, the sunset on Python 2 is actually good news, because now we have a good language for scientific computing that doesn't change anymore. So that's also a bit tongue-in-cheek. But yeah, actually, there are two reasons why Python crops up so frequently in these complaints. And one is simply that it's enormously popular. But that also means that you can't just replace it. So you and I, we might agree that maybe we should stop using Python, but it's not going to change much in the real world. I mean, it's just too heavy, too much inertia behind it. The other problem, and that's something I think one could perhaps tackle, is I don't know, maybe I'm dreaming too much, but it would be nice to convince the Python community to give up its own package managers, because this is a big issue behind the reproducibility issue with Python. But there are two issues. One is that the scientific Python ecosystem has actually changed radically at some point. It started out being extremely stable, very, very concerned about backwards compatibility. And at some point, it exploded to the point that at some point, almost everybody was coming in new. And everybody had an idea to do things better and said, backwards compatibility, who cares? We are discovering a new world, so who cares about all these old farts with their 10-year-old code? I mean, let's do something new. And that started a complete change of attitude with where you're seeing projects which are maintained at every given time by 5 PhD students, but these 5 PhD students change very frequently. And all the new ones coming in say, hey, we have a good idea to make things better. Oh yeah, it will break something, doesn't matter, it's not our problem. And this has gotten a lot of worse when Python got the mainstream language for machine learning, because in machine learning, I mean, a method that's half a year old is obsolete. Yeah? Who cares for a script that's a year old? Nobody wants to run it again. In my field, I mean, I regularly run scripts that are 7 years old, 10 years old, because I'm in research projects which between me as a theoretician and experimentalists who do experiments, I mean, that takes a lot of time. So a 10-year research project is normal. So I have a very different time frame of work. And most people are somewhere in between these two extremes. So maybe, so there's two issues. One is that Python packages break compatibility too often. I think that's hard to change because it's a social issue. But there's another problem, is the Python package managers are just awful. Building Python packages has become so difficult that hardly anyone does it anymore. Everybody depends on some pre-built binaries, which are very fragile. And I think the Python community is aware of that. Except that if you tell them, we have a solution, we have a new package manager for you, they'll just say, no, not another package manager, we have enough of those. So that might be a constructive approach. And then, of course, you can also say, let's jump ship and do something else than Python. But yeah, I think this will not solve the problem for any community. This will maybe be a good idea long term, but then what are you going to replace it with? I mean, there's no decent candidate in view for now, so not easy.
Yes, thank you. We'll go over to Matthias's last question over on Matrix, unless he types more, of course. Speculating, should a scientific study of the future run on a distribution of environments with different versions producing an outcome distribution rather than bit reproducibility? Did I read that correctly as my next question?
I think I understand what he means, so is it okay?
Then I'm going to let you answer.
Yeah, that's again a good point. I mean, I think there's two things. First thing is, I think bit-for-bit reproducibility is a worthy goal in itself as a first step. The main reason being it can be fully automated. Nix does it and Guix does it. You can run things again and again and again, check if they're bit for bit the same, and that's a useful thing to have. It's the ground layer, I would say. And I'm already having a hard time convincing my scientist colleagues that this is a useful thing to have. Because what they say is what we really care about is the next level, and that's what Matthias refers to have things which we can check to be robust until all these technical details we don't care about. So yes, I think doing such robustness checks is useful, but it's not automatable. I mean, what he suggests is, and what I also mentioned recently, is you can have tools that do the work for you, that run it for on all the combinations of version numbers for various dependencies. But there's no automatic tool that can decide for you if the result is close enough. Because what close enough means is a scientific judgment. And you can't say it's a floating point agreement to 3 decimals. It may be good enough for some applications, not for others. So in the end, it takes an expert to judge if it's good enough. And I don't think there are many experts willing to look at 5,000 numbers and judge if they are close enough to each other. So I think robustness checks of this time are useful as part of software development, as part of regression tests. I would really see it more like a regression test. So it is the developers of some package that would do a regression test like this, run it on their software regularly, and then if something comes out differently, it's one of their experts that will check if their regression test is still satisfied, yes or no. But as a tool for the general public, I think this will not find many friends. It's just, it's too heavy.
Okay, thank you. Then Bilowanik over on Matrix as well asks, how relevant are cosmic ray bit flips? Is ECC memory a requirement for scientific computation? Does Guix/Nix help with this?
Well, I think the last part, the answer is clearly no, right? I mean, if you have hardware failure, then no layoffs. When you need an error correction layer, but you could implement that in software, presumably, but that's not what Nix does. The other question is no. I think that there are studies about this. This becomes an issue if you go to large-scale computing. That is simulations like climate simulations that run for a couple of weeks on 1,000 processes. Then you get to the point that error rates from, well, cosmic rays is the most sexy sounding, but it's actually hardware fatigue is actually more important in practice. But such errors are very rare and become relevant only for very large computers and very long-running computations. And people in the computing centers, they do care about them. They do monitor them. They are handled using redundancy. So they run the same computation on several nodes and compare and check for them. So there are error corrections in place in these centers, and that's a different issue. I think this is not something that Nix could or should address. I think it's a specialist problem handled by specialists, and they know how to handle it.
That makes sense. Then Cap404 on Matrix as well asks, are there any particular groups in reproducible research community or conferences we can target? Yeah, there aren't really any conferences on reproducibility. These are small workshops, but those people you need to convince in a way. Yeah, what would be a good place? I said it's increasingly general science conferences on specific domains that have an afternoon workshops, tutorials. This is the space. How would you find them? That's a good point. Yeah, it's no easy answer to that. I've actually participated in a couple of them, and I've done trainings myself, more using Guix than Nix, but this is all small scale people that invited me because we had been in contact before. So this is not very organized. It's small scale networks. No, I don't have any easy answer for that. So sorry.
Maybe the inverse question, Konrad, are you coming to NixCon? It's in Paris. It's in your neighborhood.
Yeah, sure. I mean, the question is for what goal? I mean, what would be the takeaway?
I don't know. Maybe discuss with people how to better get Nix tooling in the hands of scientists, or things that the community could focus on.
Okay, yeah. I mean, yeah. People say interested people like me and my colleagues. Yeah, that would be an option. I think the general public scientist would not be. Would say what should I care about it? But
I would agree.
Yeah, I mean, for me personally, that would be certainly something of interest. Yeah, and I could list a couple of other people to invite, but that's a handful of specialists basically. Yeah. Why not?
Let's see you there.
On Owncast, Joff R asks, ACM has artifact review and badges for submissions that go through it. Do other fields have similar things trying to align initiatives for publishing data, analysis, code, etc.? Is this a good place to advocate for reproducibility in software environment?
Well, for advocate, this is if the journals have these kind of badges, then they are convinced, so that the job is done. You can still convince them that you have a good technical solution for them, but it's good. ACM made quite a bit of noise with that because it's a huge institution, and it was a big step forward for them to introduce these badges. There are a few other journals in various domains that do that. That's still, I think it's a minority almost everywhere, almost all scientific fields, but it's increasing. There's an interesting variant idea that's there is an institution in France, which is actually officially a support lab for research, and it's financed and run by the French research organization, whose goal is to verify, validate, certify the reproducibility of submitted computations. So you can basically send them your scripts and your data. They will give you a stamp. We certify that this is reproducible. And it's not only to outsource the work. An additional issue is that they can certify the reproducibility of computations on confidential data. Because that's the kind of, I didn't talk about it, but we all want science to be open, but if you work with medical data with which we can identify patients, this is never going to be published for ethical reasons. And so there need to be different tracks to get there. So that's why there's actually a service institution that does reproducibility checks. And yeah, I mean, I have a list of a handful of journals that do have reproducibility requirements or suggestions. They are always a minority, but the number is increasing. So the tendency is right. And yes, contacting them, I don't think contacting them is directly with the technical suggestions is a good idea, because the journal editors are basically convinced that practices must improve, but they usually don't understand the technicalities. So if you send them and say, hey, Nix is great, they say, yeah, maybe Nix is great. It's not, the gap is too large. Right? The problem is to find the intermediate layers. And I think journal editors are not the right layer.
Okay. They ask another question over on Oncast, so Geoff R again. Regarding support for research workflow, there are parallels between development and deployment of software, different needs for deployment of software than for distribution and deployment. We have dev shells, an example Nix developed for this. How close does this get to the needs for research? How is research flow different than software development?
I think the difference is that the focus on software development is the software, whereas in research it is on the computed results. And as I tried to explain in my lecture, there's a similarity in that both are the result of a computation, which you want to make reproducible, but the nature of the resulting artifact is very different. So there's no equivalent of deployment. You can deploy software, you don't deploy scientific results. They are meant for human consumption. They're packaged in things like PDF files and movies and images and this kind of stuff. Maybe websites. So there's not really deployment. The equivalent, the closest equivalent to deployment would be publication. That is putting it on a public-facing web server. That's probably the closest we can get to deployment. That's why I said you don't want these things in the Nix store. That's not useful. You want them on a web server. So the final part is a bit different.
That makes sense. Then Stringfield over on Matrix, you say Guix is more common than Nix in the scientific community. There are a couple of papers about Guix in scientific computing, but not many about Nix.
Yeah, I think the history of Guix is probably closer to science. I mean, the main founder of the project works for a French research lab. The second initial maintainer is a bioinformatician in a German research lab. So Guix was always basically driven by scientific computing. There's the Guix HPC project, which I don't know who finances it, but it's specifically for reproducible parallel computing, which is very important for scientific computing. So I think that I think Guix has a stronger foot in the scientific computation business simply by its community, there's simply more scientists in there. And as a consequence, there are more scientific software packages present in the collection, I guess. But then again, the answer is probably dependent on the field you're in. So I think it's an historical accident at some point. I don't think there is a fundamental technical difference that makes Guix more appropriate for scientific computation. It's more the community overlap that matters here.
That makes sense. And then I think, because we're running short in time, we'll end with one more question from Belowanik over on Matrix. And they ask, would a reproducible conference look exactly like the last reproducible conference?
No, of course not. I mean, the reproducible conference is one where every presentation could be redone silently and by everybody at home later on. But next year, they wouldn't talk about the same thing, of course. They would do different presentations, but they would all be archived in a way that at any point you could say, well, 5 years ago, I saw this interesting conference. I'll dig out the software and the data, and I'll rerun it and play with it and modify it and see if I can come up with some new idea from that.
Okay. Well, thank you, Konrad, for the very interesting presentation as well as the discussion at the end. It saddens me that I have to wrap this up, but I will have to wrap it up because we're hitting the time.
It's okay. I'll hang out a bit in the Matrix channel, and if people can ask questions there, and I'll be around for a while. And so
okay.
See what happens there.
So
thank
you,
you
Konrad.
for the invitation. It was a pleasure to give this lecture, and I'll meet people here again in different places in the reproducible computation universe.
Yeah, it was very nice having you as well. So thank you, Konrad. Thank you, Julia, for also co-hosting at the end. And I will be wrapping this up, and I'll talk to you guys later.
Okay, bye-bye.
Bye. So there is yet another lecture done. Very interesting one this time. So, as has become routine by now, thanks to everybody who made the Summer of Nix Public Lecture Series 2022 possible, the NLNet Foundation, the European Commission, the Nix Foundation, and Tweak get a special thanks. Thanks to the speaker of today as well, Konrad. And as they have announced, NixCon 2022, I hope to see you there as well. Don't worry, it won't be the same as the last NixCon. It's not reproducible in that sense. As well as Konrad just said, he will still be in the Matrix. So if you want to ask some more questions or just have a discussion, not necessarily with only Konrad, but just the community in general, you can head over there and ask that as well. I hope to see you in the next lecture, which will be about Nix and IPFS, if I'm not mistaken, by... Name escapes me. Oh boy, I should memorize these things. But yeah, I will see you in the next lecture next week, same time, same places, and I do hope the Oncast instance survived today. So yeah, thank you.